Thank you. This talk follows very nicely from the previous two talks, and it deals with teams. And we've heard a lot about sort of why teams are interesting, you know, that heterogeneity, and we've seen some results here and elsewhere. It improves creativity, improves outcomes in various dimensions. That's not to say that homogeneity is bad. In fact, homogeneity increases efficiency, and if you're a company, sometimes spending less resources is more significant. But what we were interested in was not to measure those sorts of things, although this is a larger project and we measured that. But here, what I want to talk about is what's happening between team members. And so these are the sort of two research questions, and in particular the second one that we normally don't get to investigate much. So this is the background or the study. We studied 57 professional engineers. Professional is defined here as at minimum of 10 years experience and no more than 20. So we kept the range. They worked in the same company, but not together. Narrowed it down. They made it quite hard, by the way. There was a company of 900 people. We struggled to get these people to meet this criteria. It was voluntary. They got nothing except a pat on the back, and it was done outside normal work time. And the task we gave them was one that they had no experience with. Actually, not many people do have experience with this task, which is to design a personal entertainment system, assistant and entertainment system for the year 2025. This, by the way, the data was collected in 2019. You can't collect this sort of data in the last 2 years. So this is the setup. Teams of 3, mechanical engineers, electrical engineers, and think aloud. That is, we collected their verbalizations and we did the sort of thing that we normally do, which is we coded up. And that gave us this kind of result, which is the kind of result that we expect to see, and that's all you can say about it. This is the kind of result we're familiar with. It doesn't tell us much about what's happening in between these people. So just to tell you what's here, these are claimed processes that are involved in designing, and this is the amount, the distribution in percentage of these 3 activities. Electrical engineer, individual activity, mechanical engineer, individual activity, and co-activity, co-design. And we can see all sorts of interesting things there, but that's not what I want to talk about. What I want to talk about is what's happening in terms of the space of ideas that these people are generating. And normally, when we talk about design spaces, we wave our hands because that's a concept. It's an idea, very fruitful, useful to talk about, but we wanted to measure it. So how do you measure the space of ideas? And here's a very simple approach. Ideas have labels. The labels are words. Every time a person introduces a new word, they're introducing a new idea. So we label this a first occurrence. So we capture the first occurrence, and you can do this automatically, of every word. And we just divide them into, is it the electrical engineer or the mechanical engineer who introduces them. The more words, the more first occurrences, the bigger the design space. Now you can do some stuff on it, which I'm not going to talk about, which is to build multi-dimensional mathematical spaces. I just want to show you the sort of network results that you can generate from the way ideas are generated and connected. The way we connected ideas, and there's many ways to connect ideas, is we took a very simple model which said if an idea follows another one within a short distance, it must be connected to it. Actually, you can show that that's a weak model, but it's a satisfactory model. So starting with that, here is the entire design space of 57 engineers. This is a design space, not of an individual, but of all 57 engineers. They're actually divided into teams of 3, so there's 19 teams of 3. And what do you see here? There's 4 things you can see here. The size of the word, which is the label of the idea, of the concept, is a measure of how many times it was mentioned. First time in each of the 19 design sessions. So, people was mentioned by, fortunately, every design session. So that's the largest. These ones here on the periphery were mentioned once. So that's the first. The second is there are links between these. And those are these syntactic links that say these ideas are connected because of proximity. There's widths of links, which is the number of times in the 19 design sessions this occurred. And then there's colors. And the colors are, I've forgotten which is, oh, here it is. Mechanical engineers are pink and electrical engineers are blue. So what do we see here? Firstly, we see we can actually produce the design space, the space of all ideas. It's an n-dimensional space collapsed onto 2D. The thing that's interesting in relation to what I wanted to talk about, which is what happens between these disciplines, and the answer is not that much. If you look at the colors here as an indication, you see that mechanical engineers are pretty concentrated here, and actually a bit further down, and electrical engineers sit somewhere else, and their overlap, which you can measure now because this is a network and there's lots of measurements you can take, is quite small. The amount of collaboration is much less than you think when you measure it. So, this is the mechanical engineers in their space, and this is the electrical engineers in their space, and there's overlap, but not much. And they contribute to different topics and different subsystems in the design of this personal entertainment system. And you can extract the subsystems by doing some not so fancy mathematics on the networks. So here's the major subsystem, and you can see there's a reasonable contribution of each, and as I said, you can measure all of this. Here's the next subsystem, which is primarily the mechanical engineers. The next subsystem is actually primarily the well, it's a mixture of both. But you see, there's not the overlap. The next subsystem is the electrical engineers primarily, and then this subsystem is the mechanical engineers. So now I'm presenting this qualitatively, but of course there's measurements behind it. Now we're able to characterize in a more formal way what's happening when two different disciplines work together to achieve a design task. And what we get out of this is that the people work mainly in their own disciplinary area, which shouldn't come as a surprise. Not only that, if you do some other analysis, what you discover is that people work mainly on their own ideas. The amount of effort put in on ideas put forward by others is universally less than you working on your own ideas, even when they're not accepted, when they don't appear in the final design. Oh, there's one more. So, different disciplines explore different but complementary parts of the design space so that they jointly generate. They don't work on the same parts. I mean, there's overlap. This rather simple network representation, which if you're interested how you get such a nice graph or network, it's called a force graph. There's nothing special about it, but it's really powerful to see. Gives us another way of both qualitatively and quantitatively characterizing what's happening in all sorts of ways when you've got more than one designer. So, for example, we've got some work done, actually the data comes from Israel, not from the Technion, it's from anyway, it comes from Israel, looking at tutors and students in design crits with the same technique. Measure first occurrences or capture first occurrences, which you can do automatically, because that's an objective measure, and the rest of it follows. Now, we're in a position to start measuring, and with measurement we can do comparisons, and that's the purpose. One of the important things about measurement is what happens as you play with this heterogeneity of a design team. How does it change the span, the size, and span is a special idea of how what's the distance between ideas in this kind of representation. So the next steps are to take networks like this and compare them to what linguists, particularly in a field called natural language programming, NLP, that comes out of AI, how they have plotted the way concepts are used in natural language. Now, why would that be interesting to us as designers? If the way designers, in generating designs, and particularly designs for things that haven't existed before, if the measurements, let's just call it measurements loosely, if the measurements of distance between ideas that designers generate are much shorter than the distance between ideas in natural language, it means they've done something different. They brought together concepts that in natural language are far apart. So now we have the ability to quantitatively measure all sorts of things. And this is all automatable, whereas all that other kind of coding, a lot of it is manual. And whilst it produces beautiful results, manual coding is tough. And with that, Julie Milovanovic, who did all the work that you see, and I finish.